Just like all the crazy people stocked up on toilet paper at the beginning of the pandemic, this video will aim at stocking up our knowledge on the stock system used in chemistry. Now in chemistry, everything is given a name with a purpose. And often the purpose is indicated inside the name itself. So when we say that something is a transition metal, that means that it's an element that represents a transition of some kind. The way to think about it is this. When you look at the first two groups, right here, 1 and 2, of the periodic table with the exception of hydrogen, you have the two groups of very highly active metals. Then from groups 13 all the way to 18, you got the semi-metals or the metalloids, which carry a lot of the same properties or similar properties that metals have, except to a lesser extent. And then the non-metals specifically, and I'll highlight this in green here, from groups 14 to 18. So on one side of the table, you got really reactive pure metals. And then on the other side of the table, on the right side, you have essentially non-metals. Now, one of the main things that distinguishes the transition metals from the highly reactive metals on the left side of the table is the high electronegativity values over here. And of course, when we say high, it's relative to all the other metals in the periodic table. And so what that does is the high electronegativity allows these guys or makes them more likely to also accept electrons. And so because of that, their charges, based on the ions that they form, can vary. And when we're looking at specifically titanium, vanadium, chromium, manganese, iron, cobalt, these can differ depending on what they're bonding with in regards to how many electrons they're going to give away. What this means specifically is that in some instances, cobalt is going to give 2 electrons away, but in other incidences, it's going to give 3 away. Iron will sometimes give 3 away, but in other incidences, it's going to give 2 away, and that is true with all the other transition metals. Now, the real reason for this has to do with electron configurations and what we understand to be orbitals, right? The path that the electron takes around the nucleus. And so because you can't always look at the energy levels vertically, sometimes it is more efficient for an electron to be removed from the 3rd shell than it is the 4th shell. And sometimes it's actually more efficient to remove an electron from the 4th shell than the 3rd shell. And we find that the case with a lot of these transition metals. Now, for the purpose of this video, we're just going to look at how to write the chemical formulas and or name compounds that contain metals from the transition elements period inside the periodic table. And so we're going to show you how do we know which charge to use, and once we've selected a charge, how we write the chemical formula. So when we're moving from the name of a compound to the chemical formula, we're going to look for the Roman numerals that are given in the brackets. And then once we identify the Roman numerals given in the brackets, that's going to refer to the charge that we're using for the transition metal. So then we're going to swap and drop with those numerals. So let's say we're asked to write the chemical formula for nickel IV nitrate. So IV is the Roman numeral for 4. So that means that we're going to use the charge of 4+. When we look at the periodic table, we see that lead could have a charge of 2+ or 4+. So the number inside the bracket, or the Roman numeral, tells us which of these charges to use. So when I look at my periodic table, and I see that this has a charge of 4+, and then nitrate, which is a polyatomic ion, which has the symbol NO3-, has a charge of -1. Then from here, we do the simple swap and drop. And check out the other videos if you're unsure of how to write the chemical formulas using the swap and drop method. But we would swap these charges, and then keeping all the rules like we did before, we place the polyatomic ion in brackets. The one from the -1 over here is not needed to be written, and so we can leave it as Pb, and then outside the bracket we're going to put 4 coming from the lead 4+. The same is true with the next one, where we have nickel, bracket, II, close bracket, oxide. So nickel can have, again, different charges, right? It could have a 1 or a 2 according to the average periodic table. In this case, because it's saying that it's 2, it tells us we're going to use a charge of 2+. So when we write the formula here, we're going to go Ni2+, and then oxygen has a charge of 2-. So when we swap and drop these, we get the following, which is Ni2O2. However, just like in math, if we can simplify, then we should. And so when we go 2 divided by 2, each of these turn into 1. And so nickel 2 oxide finally has just this formula, NiO. So let's say we're going from the chemical formula to the name. What we're going to do is we're going to look at the subscript of the nonmetal, and I'll highlight that here so that we understand. So the subscript of the nonmetal, and then you're going to place that subscript in brackets with Roman numerals. So let's say I have the final, or I have this formula here. So for example, let's say I write NiCl2, and I want us to name this. Well, I'm looking at the 2 of the nonmetal, and then I know that because of the swap and drop, that 2 must have come from the nickel charge. So we would write nickel, and I'm going to take that 2, place it in brackets, nickel 2, and then chloride. And that's the name of this compound. Now let's see another example here, where we write, let's say Pb, and then bracket NO3 2. Again, the nonmetal would be this entire polyatomic ion here. So we're going to look to the subscript, which is outside the bracket. Remember that this subscript doesn't ever change, so we don't regard it in this case. We're looking at what's outside the bracket, which in this case is the 2. So we know that it's lead. We take that subscript and we put 2 in brackets, and it's lead 2 nitrate. And this is how the stock system works. We take the reverse charge and we indicate that in brackets. Let's take a look at the next example, and I want you to try this one out yourself. Now, when we look at something like this is a little bit tricky, because if we look to the nonmetal, which is oxygen, it looks like it has a 1. The problem is, when we look at the periodic table, we see that for lead, it has 2 charges, a 2+ and a 4+. And for oxygen, it has a charge of 2-. So why would it have a 1? Well, this goes into the final category, which is, I'm going to put a star here, check if the compound has been simplified. And if that's the case, then there might be what I would call a hidden charge, right? Or a hidden clue as to what lead was used, because it could have been 2+ or 4+. So let's write the formula as if we were going to use lead 2. So imagine it was Pb2+ and O2-. And we swap and drop these. What you would end up getting is you'd get Pb and then 2 and then O2. And then, of course, you'd have to simplify this, because 2 divided by 2 would actually give us just 1. So the final chemical formula would be Pb PbO, which happens to be the one that we have over here. Now, let's say we were to use the other one instead. Okay, so let's say I decided to choose 4 plus first in order to test this out. And so I go Pb4 plus, and then of course it's O2 minus. So here, we're going to swap these, and we would end up with Pb2O4. Once again, we'd have to simplify these, and that would simplify into 2 divided by 2 is 1, 4 divided by 2 is 2. And so my final chemical formula, if I had used Pb4 plus, would be PbO2. But the one we're asking for is PbO. So, therefore, we know that the name, and that's the final question we're asking here, is it's going to be lead 2 oxide. Okay, and so we figured that out by plugging in both charges into the formula, simplifying it, and see which one gives us the compound formula that is being asked for, and then that's the charge we include inside the brackets here.